Hello, good afternoon to everyone, and welcome to this webinar titled EMWorks2D, which is a new product from Electromagnetic Works. And my name is Arvind Krishnan, and I will be your presenter today. And on behalf of EMWorks, I welcome you all, and I would like to thank you for attending today's webinar. Now, this particular webinar will also be recorded, and a link to this recording will be sent to all the registered attendees. So if you miss some part of the webinar, or if you think that some of your colleagues could benefit from this, feel free to forward the link of the recording to them. And in this particular webinar, we will have a presentation for about 30 minutes. And towards the end of this particular presentation, I will open the floor for questions, and where you can ask your questions and I will answer the same. Now, to type in your questions during any time, you can actually type in the questions. You can use the chat facility that is available in the GoToMeeting. So please enter your questions in the chat section, and they will all be accumulated. And towards the end of this session, I will try my best to answer them. Okay, with this, we will start this particular session here. Now, I would like to begin by talking about what is this product, what is EMWorks2D. Now, we all design our components in 3D. I think most of us probably use SolidWorks or Inventor or other popular 3D CAD out there. And that is how we would like to talk about new 3D designs. So that has become the norm now. So really, one question that might crop up in your mind is, why really do we need a 2D simulation? Okay. Now, EMWorks2D is a 2D simulation environment that solves magnetostatic and electrostatic problems, but right inside SolidWorks 3D CAD. Now, EMWorks2D, as far as geometry is concerned, deals with two types of 2D simulations. One is a translational invariant geometry, or what we call as the XY plane geometry problems. And the other one is the axisymmetric geometry problems. Now, further in this demonstration, I will show you particular examples where we will use EMWorks2D to simulate using both these types of geometries. Now, the way EMWorks2D handles these geometries is pretty intuitive. You can either create your 2D geometry in SolidWorks from scratch, or you can use the existing SolidWorks 3D model and then convert it into a geometry that is suitable for doing 2D simulations. At the moment, we support both electrostatic and magnetostatic. But in the future, sometime next year, we will support both AC as well as transient magnetic solvers. Now, as I mentioned here earlier, we use two innovative approaches to create 2D simulations inside SolidWorks. The first one, as you see here in the picture, is you can create 2D surfaces in SolidWorks from scratch, and you can use those surfaces to do a 2D simulation, either an axisymmetric simulation, as you see in the solenoid linear actuator example here, or you can do a planar 2D symmetric problems, as you see in the cable down here. So that's really the first approach, is to create the 2D surfaces from scratch in SolidWorks. The next approach is what I guess will be a very popular approach to most of you guys, because you would have already had your designs created in 3D. We can take an existing 3D model, and then we can reduce that model and make it ready for 2D simulations. So actually, I will illustrate both these concepts in the subsequent demos. Now we will start with the first problem that we have, which is the force on a linear actuator. As you see here in the image, this is a linear actuator that really consists of three simple components. One is the coil that you see here. Then there is also a plunger that can move about, and then there is also a ferromagnetic core that surrounds the coil. So it's a very simple linear actuator where we will try to solve using 2D axisymmetric simulation. Now this is a magnetostatic simulation. The objective is really to find out what is the force acting on the plunger when I energize the coil. And in this particular example, I will actually create the model from scratch in SolidWorks and solve the same. So let me go to SolidWorks without further ado and then look at the linear actuator model. So as you see here, when I take a section view, this is a linear actuator. So there is a ferromagnetic core, there is a coil, and there is also a plunger that can move about. Okay, so these are solid bodies, but I can very well go ahead and hide them. And now we are left with some surface bodies that were created in SolidWorks. So let me go ahead and also show the final surface, which is the air. So this is really the cross section that can be axisymmetrically revolved to make the solid body. So one technique of solving 2D problems is to use axisymmetric simulation. Now to do an axisymmetric simulation, we need to get a cross section that is symmetric about the axis. Now this is the axis and these are the cross sections. So again, this is the plunger that can move about. This is the coil and this is the ferromagnetic core. And also finally, this region surface is the air geometry. Now let us see how one can do a 2D simulation, axisymmetric simulation in this particular geometry. Now after I create these surfaces in SolidWorks, which are very easy to create if you know how they are done in SolidWorks, you can go to EMWorks2D Manager, which is again, because EMWorks is an add-in Gold Partner product to SolidWorks, you will find your 2D simulation manager right inside SolidWorks. Now in SolidWorks, you can define what is called as a study to do an EM simulation. So let me go ahead and define a study. Now to do the EM simulation, initially we have access to two different study types. We have magnetostatic, which is the default study type, and we have electrostatic. And also in the future releases, you will see AC magnetic, transient magnetic being released early next year. Now you need to create a coordinate system, or you have to select a coordinate system that is appropriate for this axisymmetric simulation. So let me go ahead and select my coordinate system here that I've created again using SolidWorks. It is really what we call as an RZ type of coordinate system, where the radial component is along the radius of the one that has been revolved around, and Z is obviously the axial along the axis. So once you define the coordinate system and select the study type, you can say OK, and this actually creates a study for you. Now the study tree, which most of you might be familiar if you're used to any kind of SolidWorks simulation or EMS 3D simulation, it's really where it is organized to do different steps in your simulation. The first step is actually to define materials to the various components. So I can go from the screen and I can pick my air surface here. It automatically highlights in my study tree. I can right click and say apply material. And from a material library that comes standard with the product, I can specify or assign various materials to various parts. So here I have assigned air geometry to this outer surface. Now this surface here is the plunger, and that is made of a ferromagnetic material like steel. So from my favorite materials, I can go ahead, select mild steel. And then again, I have another outer core, which is also made of mild steel. And finally, I have my coil that is made from copper. So now I can go ahead, apply material. I open the conductor materials and I select copper. Now, now that we are on the topic of material library, EMS has a fully customizable material library that one can use to assign materials to the various components. You can actually create your own materials and store them in the library and use them for simulation. Okay. Now, once I have created the different materials, I can go ahead and now create what is known as my boundary condition to denote the extents of my problem. So I'm going to actually create a boundary condition on the three edges here, which actually tells the program that at that particular edge, the flux becomes zero, or it's the far boundary condition as far as the domain of the air is concerned. Okay. Then we will apply coil. So to apply coil, we can go ahead and select a surface where we apply coil, and then we will also apply the amp turns that we do. So let's assume that we have about 500 amp turns of current in this particular coil. And finally, our objective here is to compute the force acting on the plunger. So we request the program to tell us the force which is acting on the plunger. So we select the plunger surface and then we request the program to compute what is known as a virtual work, which is actually the technique used to compute the force. Now that we have set up the problem, we can simply go ahead and run our simulation. Notice that EMWorks2D automatically meshes and solves the problem. In a few seconds, you're ready to look at some of the results. What kind of results are we be looking at for this simulation? First, we will start with the magnetic flux distribution, flux density distribution in my model. So you can see here the areas where my magnetic flux density is high, and also the maximum value of about 0.115 Teslas you can see in our plunger. Okay. Now I can also look at the magnetic flux as a vector plot. So I can go ahead and take a look at my flux as a vector. Now this clearly helps me to identify, I'm going to zoom in, the flux path. You can see the flux vectors and the path that it takes. And because the magnetic circuit has a gap here, there is a tendency for the plunger to move up and close this gap so that the flux lines can pass through this circuit. So you would expect a force acting on the z direction on the plunger. So let us see how we can get that. So to get the force acting on the plunger, we look at the result table and we look at the force. We have about 0.4 newtons of force acting on the plunger in the positive z direction. Notice that when we created the coordinate system, the z direction was pointing up, and that is around 0.4 newtons. Okay, so we got the force values and we have. Finally, electrical engineers would like to look at these flux as some kind of a line plot. So I can actually look at my flux distribution as a line plot. So here is a line plot of all my flux lines that I can see. So you can see areas of high flux and the areas of low flux, and you can also see the density of the lines that determine the flux at each location in my model. So these are some of the important post-processing features that are available in EMWorks2D. So one question that you might ask is, what really happens to my force if I actually say make the current as say 1000 amp turns? So you can actually do what we call as a design change or a scenario change in EMWorks2D. And then once you do that, you can as well rerun the simulation and look at your new results. So now these are the new values of the flux density. That's about 0.323 Teslas from 0.11 Tesla before. And I can go to the result table and look at the new force, which is close to about 1.6 newtons. So we had about 0.3 newtons. Just by doubling the number of amp turns, we can increase the force by a magnitude of 5 times. So we can increase the force almost 5 times by doubling the amp turn. So you can do all these what if scenarios using EMWorks2D. So now let me go back to my presentation. And just to recap, what we did is we used EMWorks2D to compute the force acting on the plunger for a linear actuator. We used the 2D Axisymmetric simulation type. We created the model from scratch using surfaces in SolidWorks, and we used the magnetostatic simulation to compute the force and the flux density distribution on the model. Now next, let us switch gears and move to something that is resembles more of a motor type of application. What we are going to do next is to analyze a switch reluctance motor. And the objective is to compute the torque acting on the rotor using a magnetostatic simulation. Unlike the previous example where we used 2D surfaces created from scratch in SolidWorks, in this particular example, I have a 3D motor that I already created in SolidWorks, and I'm now going to show you a technique by which you can do a 2D simulation, a planar XY type of simulation to compute the torque acting on the rotor if I energize just a pair of coils in my switch reluctance motor. Okay. Now to do this, again, I can go back to SolidWorks and I can go to the EMWorks feature manager. But now notice that I don't have any surfaces. You don't have to worry because we have a very neat feature in EMWorks which is called 2D simplification that allows you to select a plane and then automatically EMWorks will compute all the 2D surfaces required to do the simulation. As you see here, EMWorks is actually computing all the surfaces required to do the 2D simulation, and once it's complete, we will be ready to do a 2D simulation in EMWorks2D. So it's going through all the different components in SolidWorks, and voila, here I have an equivalent 2D model where I can do my simulation. Now, if you have complex 3D geometry and we automate this process for you, and I think that saves a lot of time and that can actually help you to do realistic 2D simulations in geometries which are inherently 2D in nature. What I mean by that is either they are axisymmetric or they are invariant across the length of the model. Okay, so as before, I start by creating a study. I create again magnetostatic study, and then here I use the planar XY geometry because usually in these type of motors, the value of the magnetic flux across any cross section does not change. So let us go ahead and use the coordinate system here that was created in SolidWorks for the X and Y and the center of the geometry. So once I create the study, EMWorks will automatically create what is called as a study tree. So just like before, we would have to apply materials to the various components. So I'm going to select all the components that are made of air, and then I'm going to use my favorite material. Notice that in EMWorks2D, I can save the materials that I commonly use as a favorite material, and I can access them during any simulation that I want. So I apply air to these things. The coils obviously are made of copper. Again, it's one of my favorite materials because I do day in and day out simulations that require me to assign copper. And also the stator and the rotor is made of steel. So I go ahead and apply steel. And the shaft is made of a non-magnetic material like say stainless steel or something. So effortlessly, I have applied materials to the various surfaces to do a 2D simulation. Next, what I need to do, just like before, I would like to tell the program the extents of my geometry. So I say at this outer edge, my flux disappears or it becomes close to zero. So we assign a magnetic vector potential boundary condition at the extreme edge of this model. Next, we will like to apply some coils. So to do coils here, I go ahead and select the surface of the coil. I can show the preview that tells you clearly what the direction of the current is going to be. And here I apply 1000 amp turns in this particular coil. Similarly, I have to apply the other terminal of my coil. I mean, it's actually a coil that is wound this way, so the current goes in and comes out this way. So I go ahead again, I make 1000 amp turns, but now I reverse my current. So when I apply, you can see that this mimics a 3D coil where the current enters through this port in the direction as shown in the arrows, and the current comes in this way. Okay. Similarly, we can do a coil at the bottom coil. So here I can apply 1000 amp turns, and last but not the least, I go ahead and select this, and as before, 1000 amp turns, reverse the direction and say. So from the direction of the arrows, you can now see that I have energized a pair of coils in the switch reluctance motor, and I would like to compute what is the torque acting on the rotor. So let me go ahead and then, so you can also, if you want to know what was the value of the coil that you applied, you can just hover your mouse, and then EMWorks2D gives you all the details concerning each of the coils that we applied. Now we would like to ask the program to compute the torque acting on my rotor. So I select my rotor components and request the program to compute the torque. As in the previous case, we use the virtual work technique to compute both forces and torques on ferromagnetic substances. So we do that. And with this, we complete the definition of the simulation. So I can go ahead as before and run the simulation. And you can see that for a complex switch reluctance motor geometry that we have, you can actually do a 2D simulation that can yield results within a few seconds. Whereas if you were to do the same simulation in 3D, we are still talking about several minutes of solution time. But within a 2D XY geometry, we can actually do this simulation within a few seconds, and you can actually look at the results and without any loss of accuracy or without any error if you do a 2D simplification. So let's see, this is the magnetic flux density, and to see the flux path a little bit more clearly, I can actually use what is called as the vector plot. You can see the vectors of the flux lines and the flux vectors distributed throughout the model. And then finally, we can also look at the flux line path plot, which gives you the density of flux lines, and that kind of gives you an idea of how the magnetic flux density is distributed inside the model. But one of the main objectives is really to compute the torque. So the torque and the force, they are available in the result table. So I can go look at the torque. So the torque is about 3.5 Newton meter per unit length of my rotor. So this way you can easily compute the force acting on the rotor of a switch reluctance machine using a 2D simulation. So let me go back to my slide, and just a recap, we used a 3D model of a switch reluctance machine. We used the 2D simplification option in EMWorks to simply extract all the surfaces required to do a 2D simulation. And this is a very useful step. If you have a complicated model, we automate this process for you in EMWorks2D. We use the magnetostatic simulation to then compute what the torque is, the torque acting on the rotor is, and also to see the flux lines and the flux distribution, magnetic flux distribution in the model. Next, we will move on to an electric problem. This is a 3-phase cable. It's a high voltage cable, and we are going to do an electrostatic simulation on a 2D XY planar type of geometry, just like the previous example of switch reluctance motor. But again, we will derive this 2D geometry from an existing 3D geometry. The objective of this particular simulation is to find out what are the electric stresses in the model and highlight the areas where the electric stresses are maximum. So let me go ahead and quickly get to the model here. I have a 3D model of a three-phase cable here, and imagine that this is a cable that can run for several kilometers, but all we need is a small cross section of this cable for us to understand the working of this cable. So hence it is invariant as far as the results are concerned along the thickness of the cable, and hence you can do a 2D XY simulation on such a problem. So as before, I can go to EMWorks2D, and again I will get an opportunity to show you this 2D simplification feature. I can select any plane that I want. So I have actually selected a plane that is halfway through the solid model, and I can allow EMWorks to automatically extract all the 2D surfaces required to do my simulation. So once it succeeds, I have now access to do a 2D simulation. So as before, I will create a study. So I can go ahead and create a study. But this time I'm going to create what is known as an electrostatic study. Now in electrostatic study, we can study the electric stresses or the electric field distribution in and around my conductors and also inside my insulators. I can go ahead and create the coordinate system and actually assign the coordinate system that is used to solve this problem and say OK. Now EMWorks automatically creates my study tree. Here is where I would apply materials to various components. The outer air surface is applied a material air. Then I use the three conductors. These three conductors are made of copper. So I can use copper from my favorite material. Then the three insulators here that surround my copper conductors, they are kind of critical. And then I'm going to go ahead and apply from my cables. I can use maybe a TFE or a perforated TFE material for the insulator. And also there's another common insulator that is probably ethylene propylene type of insulator or a cellular polyethylene. So let's apply the various insulators or dielectric material in my three-phase cable. Now I have to assign the voltages to the various conductors. So I can go ahead, and before that I go ahead and apply a fixed voltage to my one of the conductors, and let's say this works at 10 kilovolts. So I have 10,000 volts. And also, while it's the maximum voltage here, I also have about negative 5,000 volts on this conductor, and on the third conductor, again, a negative 5,000 volts. So this is kind of imagine a worst case scenario when there is a AC current, peak AC current of 10,000 volts going through a three-phase cable. So you have one of the conductors at 10,000 volts, the other two at minus 5,000 volts. So this gives you the maximum difference in potential or the potential difference in this scenario, and maybe the worst case scenario that we would like to simulate. Okay, now that we have defined all the steps required for the simulation, I can go ahead and run the simulation. And as you can see, in just a matter of few seconds, EMWorks2D will be able to look at display the results of electric stress. So let's first take a look at the electric field distribution. You can see here that the high regions of the electric stress and the value is about 3.5 million volt per meter. Now, the good thing is we have selected our perforated TFE, which is about 16 million volt per meter. So if you see here, the dielectric strength of my material is about 16 million volt per meter. But in fact, the maximum electric stress that we get is only 3.5 million volt per meter. So this kind of gives me a surety that there is not going to be a breakdown of my dielectric or breakdown of my insulator because of this worst case scenario potential difference. Okay, so this pretty much allows me to visualize the electric stresses. I can also visualize the potential. Notice that we kept one conductor at 10,000 volts and the other two conductors at minus 5,000 volts. So you can really see the potential distribution across across the various components and also in the air region. So you can look at the electric potential in volts as one of the plots. Okay. So really, I want to go back to my slide, and just to recap, we had a three-phase high voltage cable, and we resorted to an electrostatic simulation to compute the electric stress and also the electric potential everywhere in my domain. And we used electrostatic simulation, and we used a 3D model and used the 2D simplification tool in EMWorks to actually derive the necessary surfaces to do a 2D simulation. So I think this kind of concludes the demonstration part of this webinar. So I would just like to recap what we saw today is our new product, which is EMWorks2D, which is used for both XY planar geometries as well as RZ axisymmetric geometries, type geometries, because these type of geometries are you can accurately represent them using a 2D simulation. You can do them without any loss of accuracy, and you can do them at a fraction of the time that is required to conduct a 3D simulation. Now, EMWorks2D is completely embedded inside SolidWorks. Notice that EMWorks company is a gold partner certified company to SolidWorks, so our products meet the strictest standards when integrating inside SolidWorks. Again, we are able to solve both 2D planar XY geometry and 2D axisymmetric problems. Right now, EMWorks2D is available for both magnetostatic and electrostatic type simulations. But coming up next year, we will have transient and also AC simulations there. And finally, we have two techniques to do 2D simulation, basically the geometry creation of 2D simulation. Either you can create the 2D surfaces from scratch using SolidWorks and do your 2D simulation, or you can use the 2D simplification feature inside EMWorks2D to reduce an existing 3D model into a 2D ready geometry. Now finally, I know you will all be enthusiastic and you would like to try out EMWorks2D. So what I encourage you to do is, if you would like to get a copy of an evaluation version of EMWorks2D, I would request you to visit our website emworks.com and then send in your trial requests through our website. Alternatively, you can also email sales@emworks.com and request them for a trial version of EMWorks2D. If you are an existing EMWorks 3D customer, you will automatically you can access EMWorks2D. Please again send an email to us at sales@emworks.com and we'll be happy to give you a trial version of EMWorks2D. Now, as far as the product is concerned, there are a lot of learning resources that are available. We have video-based tutorials and we also have demo viewer examples. Just like our 3D products, you have a plethora of examples that helps you understand the UI and also helps you get started with EMWorks2D. Now we support both planar as well as axisymmetric methods for both electrostatic and magnetostatic type of simulations at the moment. And early next year, we will also integrate more solvers, especially the transient magnetic and AC solvers, into this product. So really with this, I would end my presentation webinar today, and I hope you all had a intuitive and an informative session about how EMWorks2D can be used to solve real-life problems like motors, three-phase cables, actuators, etc. And now I will open the floor for questions. So if you have any questions, please use our chat window and you can type in your questions, and at the end of this webinar, I will be able to answer them once I go through your questions. So if you have any questions, feel free to type in and I will answer them right now. Again, on behalf of EMWorks, I would like to thank you all for attending this webinar, and I sincerely hope that you will all be able to try out our EMWorks2D product, which is our latest product, and really hopefully it will be beneficial and can solve your real life problems in magnetics. With this, I would like to thank you all and hope to see you in a future webinar. Again, the recording of this webinar will be, a link to this recording will be sent to you to your registered email. So feel free to view this webinar as many times as you want, or share this link with your colleagues who may be interested. Thank you very much and have a nice day.